In this video on static electricity, we're going to be talking about Coulomb's law, which is the relationship that we can use to calculate the magnitude of the electric force between particles. So we already talked about what happens when we have two positively charged particles or two negatively charged particles or particles that have opposite charge. And when we have particles that have the same charge, they are going to repel each other. Well, each of these particles is actually going to feel a force that is exactly the same, just in opposite directions. So this force and this force are going to be exactly the same, but in opposite directions, because the forces are action-reaction forces, because they are Newton's third law, which means that for every action there's an equal and opposite reaction, which means those forces have to be the same. Same thing when they're being attractive. They're going to have the same force, but they're going to be in opposite direction. And it doesn't matter what the magnitude of the charge is. Say this one is +1 and this one is -1,000. It doesn't matter the magnitude of the charge. The forces are going to be the same, but in the opposite direction. So before we look at the equation, there's a couple of other things you need to know about charge. With Coulomb's, the variable for charge is going to be Q. And the amount of charge is measured in something called coulombs and is abbreviated with a capital C. A coulomb is basically a counting unit. Just like you might say that you have a dozen eggs and mean that you have 12 eggs, saying that I have 1 coulomb of charge is saying that I have 6.24 times 10 to the 18 electrons. It's basically saying I have this much of something that has charge. It could be electrons or it could be protons. But it is a counting unit, just like you learned in chemistry when we have a mole. Remember, a mole was equal to a certain number of atoms. It's a counting unit. So Coulomb's law is this equation here, and this is what we use to calculate force. So basically, when we have two different charges that we are going to call Q1 and Q2, they are going to be separated by a certain distance, that's going to be r. There's going to be a force between them. And so to calculate that force, we have a constant, which is called Coulomb's constant, and this is the number that we are going to use for Coulomb's constant every time. 9 times 10 to the 9, it's a very large number. And then we multiply that by the two charges. It does not matter what order you multiply those charges. One's Q1, one's Q2, it doesn't matter if you switch them. And then we're going to divide by the distance between them squared. So when we do this, you do need to make sure that whatever force you have is in newtons. K is a constant, that's always going to be this number here. Q1 and Q2 have to be in coulombs, and distance has to be in meters. So you can't have centimeters when you plug stuff into the equation. A couple other things to know about this. So we just talked about two positive charges are going to repel, two negative charges are going to repel, a positive and negative are going to attract. But in this equation, you do not need to include the positive and negative sign for the charge. Instead, you're basically going to be doing the absolute value, and you're going to then look at your charges afterward to determine the direction, whether it's repelling or attracting. So when two charges have the same sign, of course, it's going to be a repulsive force. When the signs are opposite, they're going to attract. Now, the electric force is very, very, very strong. If I have two 1 coulomb charges that are 1 meter apart, the force between them would be 9 billion newtons. The reason we don't see this happening, because 1 coulomb is actually not necessarily a lot, is because everything here on Earth tends to be neutral. Charge continuously moves around to keep things mostly neutral. When we're looking at charge, you're usually going to be looking at something more like 1 times 10 to the -9 coulombs of charge. So it's very, very small amounts of excess charge, because this is untenable. You can't do much with that. So let's go ahead and do an example. So in this case, we want to know what is the magnitude of the force between a positive 4 Coulomb charged object and a negative 5 Coulomb charged object when they are placed 2 meters apart. Now these positive 4 and negative 5 are unrealistically large charges. We're just using them as moderately simple numbers to practice the calculation. So I'm going to go ahead and my force is going to be equal to, I'm going to go ahead and put the number for Coulomb's constant, that's this right here. It's going to be 9 times 10 to the 9. And then I'm going to multiply my two charges. Now remember, I don't need to do my positive and negative sign. So it's going to be 4 coulombs times 5 coulombs divided by our 2 meters, and that's going to be squared. So when I go ahead and do this calculation, my answer is going to be 4.5 times 10 to the 10, so 16, 10 newtons. So that's going to be a very, very strong force. Now, another thing we can do, so this is how you calculate an actual number for the force. But one of the more common kinds of problems is going to use something we call the one-to-one rule. What it's doing is it's looking for a relationship or how something changes when I just change one of the factors in the problem. So this is how we do the one-to-one rule. We take our equation, so here's our Coulomb's law equation, and we replace every single one of the variables and constants in the equation with a 1, but we leave the math. So the K becomes a 1, Q1 becomes a 1, times Q2 becomes a 1, divided by 1 squared. So this is what it looks like. 1 times 1 divided by 1 squared. And if I do all that math, that becomes 1. This is basically my basic force. So this is what my force was without any changes originally in the beginning. Now, from here, you're going to be given a problem. For example, what happens to the force between two charges if the magnitude of one charge is tripled? So that is, one of these charges is tripled. Doesn't matter which one of them's tripled. So to figure out how that affects the force, I'm going to go to this whole thing where I have all the ones, and I'm going to take one of the charges and I'm going to triple it. That's going to become a 3. So here I have it typed up here. So 1 times 3 divided by 1 squared is equal to 3. So the force is 3 times the original force. So the force has tripled. The force has increased by the factor that I calculate. So the force is increased by a factor of 3. Here's another example. So same problem, same type of problem, but this time, what happens to the force between two charges if the distance between the charges is tripled? So this time, it's the r that's going to be tripled. So 1 times 1 divided by 3 squared. So again, here it's typed up down here. So 1 times 1 on top is 1, divided by 3 squared is 9. So this time, the new force is only 1/9 the original force. The force is less than it was originally. It's 1/9 the original force. So that's how you do the one-to-one rule problems.